Welcome back. This is part 2. You should have already watched part 1 on crosstabs, chi2, and hypothesis testing. We ended on this slide in part 1, showing that we can compare the observed frequency of each category in a single variable, compare that to the expected frequency, which is the average across that. And by doing that, we're able to test a null hypothesis. You can probably see that this is a null hypothesis. It's a hypothesis of no difference across these categories. So are these categories different? Well, we can see that they are. But is this difference likely to be caused just by chance, by a fluke? Or is this likely to really reflect what's happening in the population? So we're doing what we've done before. We're testing against a null hypothesis, a hypothesis of no difference. And so you're going to see your same type of HO, null hypothesis, and H1, an alternative hypothesis, which is often your research hypothesis. So the frequencies of correct responses are all the same. Right? So here's the correct answer, and the frequencies are all the same. This is really your null hypothesis. So the alternative is that they're not all the same, or that there's a difference from one category to the next, or at least from one category to another category. So chi2 allows us to really quantify that. And you're going to start to see in the equations FO and FE, it's the frequency of observed and the frequency of expected. So when you see FO and FE, you can translate this in your mind to observed and expected and really do quite well with that. You're going to see an equation like this. And I see most of you becoming quite confident that when you see these equations, you know that if they're a little bit intimidating at first, you're going to learn them. Because we're going to present it in English, you're going to become very familiar with what we do and what this means. And the equation is going to sort of come afterwards as a symbol of that thing. Representing what's going on there. So we're going to do the same thing we've done before with this, break it down for you, translate it into English, and you should be good to go. So subtract each expected frequency from each observed frequency. That's the first step. Square that difference. Divide by the expected frequency. Now this is a little bit different than other things that we've done, but very straightforward really. And then add up those results. Here's what it looks like. You have your correct answers. You have your FO, frequency observed, FE, frequency of expected, the frequency of the sort of null hypothesis that everything's the same from one category to the next. So FO minus FE is simply what it sounds like. Take the observed, subtract the expected, and you get 2. Take the observed, subtract from the expected, you get 4, and so on. Now you take this result and you square it. So 2 squared is 4, 4 squared is 16, negative 1 squared is positive 1. These negatives always go to positives when we square them because a negative times a negative is a positive. So negative 5 squared is 25. And once you have that, that's your FO minus FE squared. You simply divide that by FE. So what does that mean? Well, here we have 4, divide that by 10. Here you have 16, divide that by 10. And you get 0.4, 1.6, 0.1, and so on. When you get to this point, you're all but there. You're just on this last step. Add these up. And in this case, you get 4.5. That's your chi2 value. So this is like other things you've done, like standard deviation. You had this equation that's maybe a little bit intimidating, but you learn it in English. You go through the process of practicing this a few times in these columns, and you have got chi2 down. And when you see this equation, it's not going to intimidate you anymore, because that's what this is. You know you're expected, you know you're observed. You subtract, you square, and you divide by expected. And you may notice that this is FO minus FE. And here you see FE minus FO. It doesn't really matter because of the square. That's going to take out that negative value, so it's not going to make a difference which way. And in fact, a chi2 distribution is one tail. It's just one side that we're worried about an extreme value, because that square, and you are probably starting to put two and two together, chi squared, this square value is positive. It only speaks in terms of size, but not positive or negative. So this is a video that's going to help you out if you're thinking, hey, I'm still not quite there, or maybe I'd like to see this a different way. And in fact, we find in studies of pedagogy, teaching statistics, that all students learn in different ways, and the way one professor might teach statistics may not resonate with one student, but might be the best way for another. So I really encourage you, if you're a little bit stuck on this or still not sure, check out this video. I'll post it on Blackboard, and you can click on that and watch somebody else explain some of these same ideas, and their nuanced way of presenting it may be the thing that makes it click for you, or maybe just a repeat exposure to the information may be the thing that lets it click for you. So moving on to kind of the second part of this is degrees of freedom. We need to wrap our brain around degrees of freedom. And when we're doing degrees of freedom, margins don't count. Margins do not count. They're just to help us. They let us know the total, but they're not saying anything about the breakdown of the relationship. So we still use these numbers, but they don't count in deciding the number of degrees of freedom in this table. Be sure not to view this as a row and this as a column. These are marginals. They're called marginals for a reason. They're not columns, they're not rows. They're just out to the side to help us know what those totals are. And we do indeed use them, but they're not part of this idea of degrees of freedom. So they're crossed out here. Now, degrees of freedom. What is degrees of freedom? Freedom to vary. How many degrees of freedom are there? How many cells can vary freely once we know other cells? So if we had just this, would we know the number of men that do not smoke? We do indeed, because all we have to do is take 120, subtract 45, and we instantly know 75. 45 plus 75 is 120. Very basic algebra. So we can take that away, and that cell's not free to vary. It has to be 75. That's its only choice. Otherwise, it can't add up to 120. So picture these as your northern star, your guiding light, okay? And things have to add up to that. And if they do, can something else vary? Well, in this case, this can't if we know 45 is stuck. So what if we take this away? Same thing, 240 minus 65, 175. So once we know 65, we don't need this. At least we don't need to be told it. We could figure it out through some very simple math. Okay, so what if I take away one more? Now I just have one of the four cells. Okay. Well, if you look across this way, 110 minus 45 tells us the number of women that smoke. 110 is the total number of smokers. 45 men smoke. The only other category is women. We know 65. So this is degrees of freedom. I can take out every single thing except for one cell. And it doesn't have to be just this cell. It could be this one or this one. If we have just one cell, we can go out to the marginals here and figure out what goes here, and we can figure out then what goes here, and we can figure out what goes here. It's kind of like, I picture this could be in like the New York Times, some puzzle that you do. So you can go down to one cell. One cell is free to vary. Now if I don't know this, then I don't know anything that's going on in this table other than the marginals. I don't know the specifics in the actual table, these four cells. So that's degrees of freedom. And it can be a little bit complicated, okay? But to sort of simplify it, go back to that one variable, that goodness of fit analysis, and think about how many degrees of freedom do we have here, okay? Because we have this one-way analysis and we have two-way analysis, but the idea behind degrees of freedom is the same, and that's what I'm hoping you'll see here, that through intuition you know how many degrees of freedom a table will have just by backing this out, getting rid of cells, okay? and asking yourself if you still know what is going on here. So would we know that if we took E away, would we be able to figure out E? Yeah, we add these up, and we know this has to add up to 50, so we just add the last 10, right? So 12 plus 14 plus 9 plus 5 gives us 40, so E is going to be 10, and that gives us our 50. Because we know this total of 50, we can take away one cell and we still know what's going to go there, just with some basic math. What if I take away 2? Now we're dead in the water, right? Because we know that D and E have to add up to 15, but we don't know if they're both missing. We don't know which one is 5, which one is 10, or if one is 12 and one is 3, if one's 11 and one is 4. We have no way of knowing just based on these marginals and 2 missing cells. And again, it doesn't have to be these 2 cells. If any 2 cells were missing, we'd no longer be able to fill in exactly what goes in those cells. But if any one of these cells went missing, we would know how to fill in that cell based on the others. So in this case, we have 4 degrees of freedom. We need 4 cells in order to fill out every single category, or to know the frequency that goes with every single category. So here we have degrees of freedom 4. Now look in the book and think about the sort of these mathematic notations. So the book calls it k minus 1 for the one-way table, the goodness of fit. And that means the number of categories in the variable minus 1. That's how you get your degrees of freedom for goodness of fit for a one-way table. If you have a two-way table, you have C minus 1, columns minus 1, times R minus 1, the number of rows minus 1. So the number of columns minus 1 times the number of rows minus 1 gives you your degrees of freedom. I'm going to make that crystal clear for you and much more straightforward with a little trick, or a hack like we would say nowadays. So this is the cover one method. You can have any table and you cover one of the columns and one of the rows and count the remaining cells. So we're going to figure out the degrees of freedom in every single one of these tables, and they're blank, just pretend some numbers are in here, using the cover one method. Ready, go. Here we take away this, and we take away this. We have 1, 2, 3, 4 left. And you can see, using the formula in the book, 5 minus 1, we had 5 rows, and 5 columns and 2 rows. So 5 minus 1 times 2 minus 1 is 4 times 1, which is 4. And there's our 4 cells, 1, 2, 3, 4. So there are 4 cells here. We can use the cover one method and get it just as easily as we can with this mathematic notation. Here again, in this table we cover a row, a column. We have 12 cells left here. And this gives us the same thing as 5 minus 1 times 4 minus 1, which is 4 times 3 equals 12. So we had 4 rows and 5 columns. Here's where we get our 5 minus 1 and our 4 minus 1. We get the same thing using the cover one method. It works with a 2 by 2 table. Cover one row, one column. You have 1 cell left. So this is also 2 minus 1 times 2 minus 1, which is 1 times 1, which is 1. So you can cover a column and cover every time, just cover one column and one row, count the remaining cells. That gives you your degrees of freedom. And it's just a little hack. It's a little trick, kind of like when you learn to multiply 9s by putting down one finger, and then you have everything on one side for the tens place and everything on the other side for the ones place. It's just a hack, a quick way to do this. And we usually don't have tables much bigger than this one here, something like a 5 by 4, 5 by 5. That's a pretty big cross tabulation. So hopefully this has you well under your way on understanding degrees of freedom. And in the next video, we're going to see why that's so important, because without degrees of freedom, our chi-square value that we compute is meaningless. So I'll look forward to seeing you in the next video, and good luck with your quiz.